actually Thursday as well. Basically put together the things we have discussed before in object-oriented terms. So far, we have collected your homework one. We got a couple of submission, which I already forwarded to the grader as well. The project manager is looking at your requirement document, I hope. The timeline I gave them is that they should try to get those things back to you this week. Okay, but I don't have control over their life because they are also students. So I'm just saying my recommendation is the timeline for them is to get those things back to you by this week, so that you can look at your requirement document and if necessary fix certain things in the design document. Okay, so we are entering the half point of our class. All right, so you can see that half point we are essentially looking at requirement and design. Those are the two big things we have been looking at. So requirement basically is you need to figure out what you need to implement in terms of features, right? That essentially is what your system exhibit to the outside. And design is pretty much how are you going to implement those features in terms of what components you have and how you pick, how you define your components in terms of classes, or also you need, in the detailed design we're going to talk about today, you need to pick up your algorithms, right? Basically, you have the way to write down your algorithm so you can give to another teammate to implement. All right. So in terms of quality of document and necessary of detail, our rule of thumb is look at the level of experience we have here on our team. Our team is our class. And what would be the detail level you would like to expect from somebody else in terms of requirement document so you can continue on into the design stage? What would be the detail you would provide in your design document? So your document can be passed on to him and he can take up and start implementation. Certainly we can have once a day stand up or something like that to think and ask questions and once in a while. But if you need him, for instance, if you need him by your side 6 hours for the day, then that's defeat the purpose of having a document, right? So essentially then you actually reduce the work productivity from 2 to 1. So that is definitely not ideal. Certainly it's very hard in terms of collaboration to have productivity of 2 in absolute value because you do need time to communicate and talk. But if you drop it to 1, it certainly defeats the purpose of having teamwork, right? You better just let him do the work and pay him twice or give him twice as much time, right? The goal is you're above something like 1.6, so you are actually making good progress in terms of time, right? So we are paying more money to basically buying time, right? So essentially that's what a rule of thumb in terms of content of documents and the quality of document. Basically you have to look at your level of expertise within the group. For instance, our group. Or if you look at a different group, have been working together for 10 years, in Google, it's probably going to be different, right? So you cannot use the same measuring stick for both teams, right? For us, we basically say, for the size of system we are looking at, that small chat app with 2 components, major component, one on the client side, the other on the server side, and so that kind of complexity, you should be able to convey the requirement, the design, the test plan using documents, and basically achieve roughly 1.6 and above productivity out of 2 people, right? So that is essentially our goal of having software engineering and basically enable teamwork. If you have no software engineering practice, then pretty much you have no teamwork. No teamwork, you'll be a lonely developer working on that project for good. I mean, that is not a way to scale up. Okay? All right. So today we're going to continue on the design document. And you can see that from our quiz, we are gradually crossing into algorithm design from data structures, right? But we have looked at data structures. We basically had a quick recap of data structures in the first couple weeks. We talked about the fundamental ones like linked list, which you did at first. Then we did array, how you utilize array. Array is very fundamental. Linked list is very fundamental, and array is crucial, right? Basically, you can see that linked list is not built into your language, and array is built into your language. So array is more fundamental in some sense. We look at stack as well. We know what is stack. First in, last out, last in, first out. We look at queue, which basically is first in, first out, right? Queue is different from linked list in the sense that queue, you cannot really remove things from the middle, cannot insert things in the middle. You have to basically insert from tail end and remove stuff from front end, right? So that is queue. Then we start looking into trays. That's the next level up, right? If you have linear structure like linked list, stack, and queue, naturally the next step is into trays, right? Tray is the reason to have tray is to organize information in a way you can search it quickly, right? That's why binary search tree you have all learned before. You know that if you scan an array, a linked list, basically your running time is going to be proportional to the number of elements in the array or in the linked list. That is slow, right? If you have a large array or large linked list. However, for binary search tree, it's going to cut it to log n, right? So when your n is big, the difference between n and log n can be significant, right? So essentially, for instance, if you have 10 to the power of 10 element in your array, if you do a linear search, it's going to take you 10 to the 1024 to get to the bottom of it, right? So, but if you use a search tree, it's going to be 10, right? So essentially, that is the difference between a tree structure and the linear structure. Right now, we are actually adding more features to our tree. There are a lot of things to add to the tree. Last time we did basically a search, a modified search, which is print out the depths of the tree, which is pretty easy in some sense. If you just do a search over a tree, you have a variable keeping the maximum depth. Then once you're done with the search, you have the number print out. That's it, right? So that is essentially whether you do a breadth first search or depth first search. That's up to you, because in this case we have to basically search all the elements to make sure that you hit all the branches, right? So we are going to add some more algorithms starting today, right? Then you can see that we are crossing over from data structures to into algorithms, right? So once you have tree and graph, I mean most fancy algorithm always on the graph, right? Graph will come later. A graph is basically the most complicated data structure we have right now, right? Because graph is arbitrary, you can do any graph, anything will be a graph, right? So all computer data can be represented pretty much as a graph. The graph is the most complicated one. But for your level, I think you should be fairly comfortable with linked list, array, stack, queue, binary search trees. I mean, tree have many different flavors which are pretty complicated, as you may have already seen. But the basic things are binary search tree, right? Those are all the algorithm related to binary search tree. You should be just like, okay, it's on the top of my brain. I can use those things any time. Okay, that is the goal of our quiz practice. Get you refreshed on those data structure and starting to think about the complex, a little bit more complex algorithm as we go, right? Why are we doing this? Because, I mean, to be honest, I mean, at this stage, for all the projects you're doing for our classes, I mean, those data structures should be more than enough, right? They are the fundamental algorithm. You should use them. They should solve your problem. And gradually, as you move on and on, I mean, you're going to learn many more complex data structure, which are essentially some kind of composition of the thing we talk about, linked list, array, stack, queue. Then essentially you can assemble all these things together with graph. Then you have your ultimate, most complicated data structure, which may be called Facebook or Google or Amazon, right? Those are essentially assembled all the fundamental data structure we have, right? That is also how our programming language is structured, if you will. I mean, fundamentally, your Java support those very basic data structures: integer, float, string, array. Then you can define classes. With classes, you can package all these fundamental data structures together to become a bigger and bigger data structure, and that data structure essentially going to become, your class are essentially going to become some kind of graph, which is essentially contain everything, right? So essentially, the way you learn all these data structure and algorithm should be like this. Should go hand in hand with your programming language, right? Doesn't matter what kind of programming language you use. What the fundamental to you are these data structures and algorithms. So that's why I don't care you know Java or not before my class. If you have learned those fundamental algorithms, picking up those Java features would be fairly easy, because we are not requiring you to have very much in-depth tricks about Java. It's mainly the basics. All right. So that is essentially where we are right now in our class, and also the content-wise, we're going to talk about design. Design here, essentially detailed design. In one sentence, it's basically you are give the attributes, the data type, define the interface in terms of methods, and pick out the algorithm for each method. That's it. Actually, our class is done in terms of content. Now we're just going to look at examples, right? Pretty much the thing you do in this stage is you give attribute type, data structure type to your attributes. Then you define the methods as an interface for accessing these data structures. Then you provide the algorithm for each method. For most methods, the algorithm is super simple. For instance, your getter and setter, you don't really need an algorithm. You basically just get the value and return, right? So your search algorithm is a little bit more involved, right? I'm searching for element in terms of linked list, in terms of array, linked in terms of stack, in terms of queue, in terms of tree, in terms of graph. That involve different complexity. That's the algorithm we have been practicing in our quizzes, right? Then you have other really application-specific or class-specific methods. Those are the things you have to piece together by using basic algorithms, right? Basic operations and basic algorithms, okay? That is how we scale. Basically, you divide and conquer. You take all these small ingredients and elements and put it bigger, right? The same way, so this is how we cook, how we build this building, how we build a road, how we build a mechanical part, how we build our aircraft, which is not reliable nowadays, right? So it's all about starting from ingredients and gradually building up. And certainly the same thing with our program building. You're starting from very basic elements and building to bigger and bigger. And all the architecture design and the detailed design we're talking about here are actually partitioning. We are actually dividing, right? Dividing to a certain extent, then we can put them back up together with the basic elements. That is how we work. That is how a team works. So essentially, that's going to be how we actually can organize, for instance, all the about 20 people here in our class together into an effective team. That's going to be what we do, right? whenever you join that capstone project, 7 or 8 of you will actually become a team, basically the same level of people like you are, maybe a couple turn, right? Then how they assemble you together, basically follow the tricks we have been discussing here, right? Partition into small enough pieces, give each one of you something to work on, then come back with your final finished product, because we have already determined the interfaces. I mean, we assemble the system together according to their interface. That's what you are doing with your client and server. Okay? You are taking your client and your server and you're trying to assemble them together. I mean, that's something you can do a perfect job with your client. You can do a perfect job with your server. If you don't have a good interface defined between them, you can't assemble them together, right? That is the critical part in terms of divide. If you don't divide the right way by providing the right interface, you no way you can come back and assemble them together. Okay. All right. So that is a nutshell of what we are talking about here. So let's look at basically examples. Quick recap of what we talked about last time. Operation-oriented design. This is still relevant, as I mentioned last time. If you become a C programmer, a Fortran programmer, any classical, non-object-oriented programming scheme today, pretty much you have. I mean, you may also program in terms of assembly language. I mean, this is still the approach you use. Okay. Although they are very classical and they are old, maybe more than 60 years old, but hey, they are still used for today. Okay, if you're programming in C or Fortran assembly language, this is the way to go, right? If you are going to construct C, Linux utility, a command or something like that, if you are going to do that, this is still the approach you would have to follow. Pretty much. So if you write say some kind of command just like your ls or cat, something like that, this is the approach you use. Okay. Data flow analysis. Then essentially you partition the system into 3 parts. One handling the input, one handling the output, and one do the transformation. Right. Very simple concept. Right. You get the idea is you get data into the computer, into the system, then you process the data, transform the data into something, then you dump it out, right? You may say, this sounds too simplistic. Why is it still useful? If you look at it, this is our machine learning system. You have input in, you process the input, you dump the result out. The input can be your image, and output can be the classification of those images, or segmentation of those images. Right? Same thing, same idea, right? Even such a simple structure, it is still the right model, even we use today. For instance, the point of highest abstraction in terms of machine learning system, right? You have a representation of your image, you have a representation of your network, then you process the image, and your highest level of abstraction, that's probably the segmentation, image segmentation. Then you dump them out into something that you can utilize for different job, right? Even for this, so it's for data machine learning system that's up to date, the most advanced system we have right now, you can still do data flow analysis and come up with their structure. Okay, that's why although after 60 years, this is still very much relevant to us. All right, you can further decompose this, and eventually you actually decompose them. Why you are doing this decomposition? Because you want to make this small enough you can give somebody to work on. Either that person you, or that person is your teammate. Okay? So the reason we are doing this, come up with such a partition hierarchy. So the goal is to make sure that we can assign this to somebody to work on. Then because we have assembly rule here, how they should be assembled together, then we can take the work product of each person and assemble into the final system. Okay, so again, how big a module should that be? That's really depend on capability of your team, right? Your team can handle bigger component, you can give them bigger task. If they cannot handle bigger component, you have to have somebody to do a more detailed partition so that, hey, there's nothing can go wrong, right? So you can stay here and just say, okay, I'm just going to give this to somebody to work on, that's all. Or you can go here and say, oh, that's too big a component. We're actually going to partition them into smaller sizes and make sure each one of them can consume one, right? Here you are being educated to be able to take on one of those, which make you a useful element to use in software engineering industry. That's where you get your entry-level job, right? If they give you something you can take on, yeah, you go work on that, and then somebody can come here and assemble all these things, three things together, who are more experienced, right? So that's how basically how it works. All right. So here is how if you are going to communicate again. We talk about use cases in our requirement stage, but by no means use case diagram is the only way you can communicate your requirement, right? You can use user stories. You can use just tables and a list of features. That's up to you, but just use case is one way. And here, when we are at the point of detailed design, how do we write down those design so that we can pass on to each other to work on? Okay, what are the possible formats? So we can use tabular approach, or we can use pseudocode. And you can see that we are now we are now connecting with what you have learned in 100 level classes and 200 level classes. We are crossing into, so this is actually the interface. We actually link with what you would have learned before. Okay? So tabular format,